Hi, everyone. I'm Yang Liu. I'm a research scientist at Lawrence Berkeley National Lab. Today, I will talk about an auto tuner called GPTune that we developed for auto-tuning exascale applications. Here, I listed some of our GPTune team members. So as we probably all know, that auto-tuning means finding a set of tuning parameter configurations that would optimize an application's performance, such as runtime, memory, or accuracy, and etc. So here I listed a few of the HPC codes that GPTune considered. So ranging from dense and sparse linear algebra libraries, finite element libraries, algebraic multigrid methods, and fusion simulation codes. So here, beta is the number of tuning parameters that we identified. So you can see it's roughly on the order of a few to a handful of tuning parameters. So the obvious difficulties for tuning these applications are as follows. So first, the object function is usually highly non-convex, and there's no gradient information available. And the search phase can also be complicated, meaning it can contain real, integer, and categorical type of data, and also some weird type of constraints. Furthermore, the cost for obtaining a single sample is expensive. In the sense, it requires a large number of cores and for running for a long time. So we typically have very limited budget of performance data. And also, these HPC codes are oftentimes not fault resilient or noise resilient. And finally, the best tuning parameters are strongly machine dependent. So there's very little you can reuse for the result on a different machine. So the strategy of GPTune is twofold. So let me reiterate myself. So for the first few challenges, meaning hard object functions, hard parameter spaces, we are considering black box methods. So non-gradient based methods. So those could be either model-free or model-based methods. So particularly here, we're looking at a model-based methods, meaning we're building a cheap surrogate model for the black box function, and we're minimizing the object function using these cheap models. And for the following challenges, such as, basically, meaning we have very limited number of good quality performance data. So the idea is really to find ways to better utilize these data. And there's two approaches. One is we are leveraging this multitask learning algorithm, or MLA, on correlated tasks and machines. The second is constructing a historical database and supporting checkpoints. But we will not talk about that part in this talk. So let's first go through the overall structure of GPTune. So let's first give some definitions. So first we have this task parameter input space, or S, which is a space of set of parameters that define a task. For example, for scalable QR, we can use the row and column dimensional metrics to specify a given task. And then we have the tuning parameter space, PS, containing the tuning parameters that we want to tune. For QR, that could be row and column block size, and assuming that a total number of core counts for a single application, then we can also use the total number of MPI counts, and also the number of MPI row processes as to actual tuning parameters. The output space is obviously the space of the object functions. So by default, we just use the runtime. But as you will see, we can also consider a bunch of them altogether. So the GPTune algorithm falls into the category of efficient global optimization, or EGO. So the basic framework workflow is we have sampling, modeling, and search phases. For the sampling phase, we're generating input and initial tuning parameter samples and call the expensive applications. With these initial samples, we can build a multitask Gaussian process model, which is parameterized by some hyperparameters. Once the GP is built, we can search the model using some kind of acquisition function to find the next sample point. And then we sample the function, then move back to the modeling phase until a total number of budget is reached. For the sampling phase, it's so for the multitask based sampling phase, we will first identify a set of tasks. This could be randomly generated or pre-selected. Then for each of the tasks, we will sample some initial pilot samples in the tuning parameter space. And there, I have to mention that there are trade-offs between how to choose the number of samples and the number of per task and the number of tasks, but we will not go into details here. Now for the modeling phase, this is some basics of the Gaussian process for single task tuning case. So suppose the object function is yx and fx is just a Gaussian process model of that. Well, assuming that the Gaussian process is zero mean, and the covariance is a simple classical Gaussian kernel. So these are the hyperparameters. So I need to mention that any type of tuning parameters, real, integer, or categorical, can be handled in this way by just mapping it to the real values in interval of 0 to 1. So here is a simple example 1D analytical function showing in blue, and with the red sample points, we can build this Gaussian this GP model, which predicts the mean of each observation point shown in black, and the confidence intervals shown in shaded gray, along with each observation point. So once the key feature of GPTune is multitask learning. So we can actually extend the single task GP to a multitask case. Say we want to consider a set of delta different tasks yi, and let fi be the Gaussian process model of each of them. We can use the so-called linear coregionalization model, or LCM, to build a joint Gaussian process on all these delta tasks. So each of the fi, assume it's a linear combination of the so-called latent function uq, which is itself is also a Gaussian process with its own hyperparameters. So this linear combination coefficients and these parameters can be trained by, for example, using BFGS or other type of optimization algorithms. So once the model is built, we actually have this kind of this surrogate model for each of the tasks, and then we can define, for example, the expected improvement as an acquisition function on each of these surrogate models, and we can minimize this EI through, for example, evolutionary algorithms to find the next sample point. So that's actually the overall framework of EGO in GPTune, and we actually implemented that thing in parallel, discrete memory parallel. So the way we view it is we always want to call GPTune with one MPI, such as the blue blocks showing here. So in each of these phases, we can use the model of MPI spawning to dynamically launch more than one MPIs for different purpose. For example, for the sampling phase, we use one MPI to spawn expensive HPC applications that can have varying decompositions of MPI counts and the OpenMP threads. For the model phase, we also use the spawning to accelerate the computation of the most expensive part, which is the inversion of the covariance matrix. In the third phase, we also accelerated the tasks we also parallelize over the tasks to accelerate that phase. So here is some parallel performance result. Consider this very simple 1D analytical function ytx. T is a task parameter. So this shows that 4 values of t give you somehow like 4 different correlated functions. So we generate actually 20 of those, and so we'll consider either using one MPI for the whole tuning or 32, and we're measuring the search phase and the model phase by increasing the number of samples per task, epsilon total. So we can see we can get good speed ups. So the first real application we tested is QR. So here we're assuming that the number of task delta times the number of the samples per task epsilon total is fixed. So we can set delta to 1, that means single task, or delta to, for example, to 10, that's multitask. So for single task, we'll consider this specific matrix dimension. Multitask, we are generating 9 other matrices with different dimensions. So for QR, we are using 2,000 cores. So this is the performance. So we're sorting these 10 tasks by their flop counts. So this is the one in orange, that's the single task one. So this shows both the worst case and runtime and best runtime. So you can see that MLA give you a similar minimum, and also it can also give you also give you some tuning data for all the other tasks. And when you measure the flops performance, it's on the order of T flops. So the right one is a scale-back SVD on a much smaller matrix with a smaller number of cores, but the conclusion is basically the same. Then we can, so if you look at the breakdowns of these 2 experiments, since we're generating for MLA, we're generating multiple random tasks of smaller sizes, it actually requires a smaller, significantly smaller overall tuning time compared to a single task. Then we can also compare with other available tuners, for example, Autotuner and HP Bandster. So we look at 2 metrics here. 2 performance metrics. The first one is the final performance, which is really the ratio of the best runtime returned by each tuner on each task. So we consider QR on 10 matrices, 2,000 cores, and SuperLU on 7 correlated matrices, 1,000 cores. So the higher these values above 1, the better GPTune overperforms the others. And so for both, so for QR, we can see it's actually 70 or 80% of all tasks that GPTune is better. For SuperLU, it's 60 or 70 over 7 tasks. Then we can also look at the anytime performance, which basically measures the historically best runtime at any point of the MLA iteration. So here we're considering the hyper example for solving a Poisson equation on a 3D regular grids. And we can use the grid dimension as a metric for the as task parameters. So these columns are actually final performance, and these are anytime performance. So the smaller the better. So this is GPTune, OpenTune, and Hypermaster. You can see with various settings, GPTune constantly overperforms the other two. Now we have time to mention some of the more advanced features of GPTune or more recent development. So the first one is the support for multi-objective tuning. So it's not hard to see that if we set the dimension of the output space to be larger than 1, then that's multi-objective tuning. We can actually build one LCM per objective and use the multi-objective search algorithm in the search phase for the next few of sample points. So the example is SuperLU. For the multi-objective, we're considering both time and the memory of factorization. And for single objective, it's either time or memory. So we can also consider both single task and multitask. So for single task, you can see that the black ones are the Pareto front returned by the multi-objective tuning, and this and it's quite comparable to the single objective tuning, and all of those are much better, way better than the default tuning parameters here. And this is the multi-task. So the solid are multitask, the dashed are single task, and the multitask can also beat or at least no worse than the single task tuning results. The second one is feature is we can incorporate the coarse performance model. For example, consider QR. We can have this simple performance model y tilde tx. T again is the task parameter, meaning m and n. X is tuning parameters. So so it's actually linear combination of the, for example, flop counts, number messages, and volumes, which all have like nice formulas here. And it's so we can actually incorporate such kind of a performance models into the GP model we talked about previously by just replacing a tuning space point x with x appended with this y tilde. It's worth mentioning that y tilde can also have its own hyperparameters, such as those highlighted here. The way we can handle this is every time we generate a new sample, we use the new samples to first update the performance model, I mean its own hyperparameters, then incorporate this back to the modeling phase, the GP model phase. This result is QR on 5 tasks. So so it's the ratio between without and with the performance model. So the higher above 1, the more beneficial with the performance model. So see that's actually the case, particularly when the number of samples per task is small. Then we can also consider multi-fatality tuning. So the idea is combining the ML algorithm with the so-called multi-armed bandit strategy. So the multi-armed bandit strategy will generate multiple arms, and each arm has a starting fidelity, and it will generate some initial samples on that fidelity, then call this so-called successive halving to keep boosting the fidelity level and reduce the number of samples until you reach the desired fidelity. So we can think of this algorithm in the set of a multitask setting. For example, this is a high-level like view. So we can have multiple arms and multiple tasks, and each arm has different sample sequences. And we can use the LCM or MLA to actually build models across different arms and tasks to help generating better initial samples for the successive halving. So as an example, consider a hyper example again, but here we're tuning the convection diffusion equation. So we have the coefficient C and A, which can be used to define a task, and not like the previous example. Now we can use the discretization size as a fidelity definition, a fidelity metric. So the left figure measures this multi-fidelity MLA versus hyperbanster, which can be used as a multi-fidelity single task. And the right is again this algorithm versus multi-task but single fidelity. So the red are the proposed one. So you can see it's like 90% or 70% overall of the tasks that this algorithm is much better. And finally, I want to mention the support for GPU tuning. So we can actually also handle multiple GPU codes. For example, superior GPU factorization. So here we can add a few actual parameters that are GPU related. So this is a result for single GPU. This is a result for 16 GPUs. So the takeaway is the default parameters is actually meant for certain CPU structures. And you can see after the tuning, GPTune tells you that the best parameters for GPU, those are like more GPU hardware related, meaning you would like to generate a matrix that is denser and have better flop performance at a cost of maybe more memory. So as a conclusion, so there are a few ongoing and future works we don't mention and haven't mentioned. One is the support for historical database and checkpoints. Second is we're also considering clustering-based GP for handling non-smooth objectives, which is pretty common in practice. And we can also combine GPU with neural networks, and we can also consider fast linear algebras for accelerating some of the expensive operations. And it's also worth mentioning that GPTune is a publicly available software. We also have a good user manual. Finally, this is some acknowledge page, and I'm happy to take any questions.